So how many of you have heard of Shazam? Shazam, yeah? Do you guys have it on your phone? If you do, can you take out your phone and help me Shazam this music? Can you guys pull out your phones, please? I need help, come on. Let's take out your phones, guys. I'm gonna play you a song and really need some help here. And this song is an ode to the Super Bowl yesterday. It's the same artist. So can you help me?
Do you ever feel like a plastic bag?
Anyone?
Drifting through the wind, wanting to start
All right,
again.
did your phone get that?
Do you ever feel?
All right.
Feel so paper
Great,
thin,
excellent.
like
So,
a house of cards, one blow from
we could hear the whole song, but I'm going to stop now. You just used a GPU-accelerated HPC cluster in the cloud. Okay, and the reason I wanted to show this particular demo was a lot of us from the HPC industry have talked about how HPC touches our lives, and today it actually does. There are multiple applications on your phone today that are using the same HPC cluster architecture in the cloud. And for example, this cluster that is used by Shazam has the same architecture. It has GPUs. If I'm not mistaken, actually, it's a Supermicro server. And it has InfiniBand in it. So it's a cluster with InfiniBand. And in fact, in the later half of my talk, I'm going to discuss something called deep learning. Deep learning is completely running on HPC-style clusters. These are clusters with up to 8 GPUs per server. Most of them have InfiniBand in them, so very high-speed interconnect. And these are all kinds of applications that are impacting us, right? So we'll get to that in a minute. Let's start going here, and let's hope the clicker works. Maybe not. Well, there you go. It's just a little slow. So just, I think most people are familiar with GPU computing, GPU-accelerated computing, but I want to make something clear that GPU-accelerated computing essentially accelerates what was otherwise going to run just on a CPU. It doesn't replace a CPU. It's like a turbo engine in your car. It makes things go faster. And it only makes things go faster, which can take advantage of hundreds or thousands of small processing cores. So it's a different style of processing. The analogy I usually use, to explain this in a simple way is if you want to go shopping at a grocery store, driving to the grocery store is a sequential task. There's really not much you can do to accelerate that. You choose a path, you go down that path, and you can get a faster car, lower latency core, right? A faster core, and you can get there. Once you're at the grocery store, you can tear up the list. And for my case, once my kids are old enough, I can tear it up into 4. And the 4 of us can go through the grocery store and shop. That's parallel processing. That's what GPUs are good at, right? We can, with our thousands of cores, take, for example, an image and process on every pixel on that image simultaneously to get you an answer faster, or a weather simulation, or a molecular dynamics simulation, and the list goes on. Now, this is interesting because the impact of this is best actually explained by some work that came out of Stanford. Google did an experiment on using about 1,000 CPU servers, and they essentially ran YouTube video through these servers. They called it the Google Brain Project. And in the end, the computer model that they were running, which turned out to be a deep learning model, was able to recognize a particular object in those YouTube videos. Yep, you guessed it, it was a cat. The model was now able to recognize cats. The year after that, folks at Stanford in the AI lab, Andrew Ng and his team, did the same project using just 3 servers with GPUs in it, right? Google, anybody. That was a big difference, right? How many companies can afford a 1,000 server farm versus how many university professors can afford one of these, right? That was a big impact, right? Again, this was a deep learning impact, but it tells you the nature of why GPU computing is interesting at all, right? Why are so many people kind of hooked on to accelerated computing? Why is it spreading? This is one case study. In fact, what we see is there is a very wide domain of areas where we're seeing an impact of accelerated computing. We definitely see the seismic imaging industry for oil and gas, and they are trying to figure out what the subsurface looks like. Where are the oil deposits? Where are the gas deposits? Financial computing, all kinds of research activity in higher ed and supercomputing labs. We heard about some of the ways, Addison talked about some of the ways the government tries to keep tabs on us, usually for homeland security, and in those cases, GPUs are extremely valuable. And then the consumer web guys. We have case studies from who's who right now of how they're using GPUs to provide services. Baidu has, for example, apps on your phone that can translate from Mandarin to English and vice versa. We're beginning to see apps that can translate text. So you hold up your phone to a piece of, for example, Italian, and what it shows you is English. Right? So the camera is taking a picture and it's translating it to English in real time. Right? So you're seeing all kinds of these consumer apps that are using a lot of high-performance computing in the cloud, and in many cases powered by GPUs. And the economics of the GPU is what really makes it interesting. So we published a catalog of all the applications. You can get it from our website. So this is just to show you kind of that there is a lot of momentum behind this. In fact, wow, Addison walks in just as I show his data. Right, so the Intersect 360 group ran some surveys, and this is 2013. Addison, I appreciate if you could send me new data on a new survey. I'm sure you do. So half the systems this year. Okay, great. So I think if the value proposition is there, right, the benefit is there. We're seeing the momentum. I think a lot of you have heard about GPUs. This is data from user surveys that Addison and Intersect 360 has done. We've seen similar data come out from IDC, if I may pitch his competition as well. Now, the other, one way I measure both our success and the momentum of the market, and I'm so sorry I missed Supermicro on this slide. I should have had you guys on this. But one way to measure this is how many servers out there now support GPUs, and how much of an investment are the OEMs or the big server manufacturers making into GPUs. I think we heard very eloquently in the last session about what Supermicro is doing, but you also have all these other server manufacturers who are putting 8 GPUs at times in a single server. And these are mainstream servers from Dell, HP, Quanta, Supermicro, Cray, you name it. There's about 100 servers that we have on a list right now. And this, again, just shows you customer demand. That's all it shows you. These people design servers because customers ask for them. Now, if you're familiar with GPUs and you've been following them for a while, the one thing you might have seen that has changed is as we have built this ecosystem, it's really become a platform. The definition of a platform is that other people build on top of it. We started with 2 things. One was a GPU with an architecture which was massively parallel, and the other was a method to program it in an easier way than it has ever been done before. This was the parallel programming model that we called CUDA. We inserted this parallel programming model into C and C++, and then eventually Fortran. And today it's available in Python and Java and many other things, right? But the point was we gave you a basic architecture and programming tools. Since then, we've kind of, in fact, almost gone in this way, which is compilers, debuggers, profilers, libraries, not just from NVIDIA, but vendors and partners who partner with us. All kinds of system management software, all kinds of interconnect technologies, and all kinds of OEM systems. So what you really see is that there's another ecosystem that's formed around the accelerated computing, around accelerated computing. And the other thing we changed a little bit over the last 1 year is we used to be only on x86. And as we see ARM64 and OpenPOWER and IBM's Power stuff get into servers, we are broadening that ecosystem. In fact, the same software that you write or have been writing on x86 will just work on ARM64 and Power. So you now have a common parallel programming model across all of these three architectures. That's extremely valuable, especially as future languages like C++ pick up support for accelerators. We've also expanded the way you program the GPU. We started by adding these kind of explicit parallel programming constructs into C, C++, Fortran. We've then expanded into the directive-based approach. So you're familiar with how OpenMP is used for multi-core CPUs. There's a similar open standard for accelerators called OpenACC, which is, again, directives that allow you to map a program to GPUs or to other accelerators. And then, of course, the library ecosystem keeps getting richer. The latest libraries that we've released are a deep learning library, a deep neural network library, and a sparse matrix library. I wanted to touch upon something that I believe is extremely valuable for the HPC community, and I believe that we haven't done enough on. And as an NVIDIA person, I'll say that NVIDIA is trying to do a lot more into visualization for HPC. So a lot of us have heard about in situ visualization. It's fundamentally the notion that as you simulate, you visualize the data. And typically what happens today is you simulate, you store, then you have a separate visualization cluster where you go and visualize afterwards. The value of in situ visualization is that, a long time ago, I was a grad student, and you would look at the data afterwards and go, damn, the last 2 days of experiments were useless because on day one, I made a mistake or there was something I found that should have changed everything in the next 2 days. And in situ visualization allows you to do that. As you simulate, you can see what's happening, and a picture is worth 1,000 words. We did some work with the University of Illinois at the NCSA Blue Water system, which has NVIDIA GPUs in it. And they, for the first time, visualized a chromatophore. The chromatophore is what transforms light into energy in plants. And for the first time, they've been able to build a complete model of this. So just simulating this was hard. Now they're simulating and visualizing it. And the advantage of this is that you can actually see this, and the green is where the light is shining, by the way. So it's an interactive model. So when you can actually move it around and shine light on it, and it reacts to the light. It's a wonderful demo. You can come to any show where NVIDIA is presenting, and we have the demo running. And then you can peek in. You can kind of double click in and try to look inside the cells and learn more. We did some work with the CSCS Supercomputing Center in Switzerland, and they actually ran what we believe is the world's largest in situ visualization. This was about 5,000 GPU accelerated nodes on a Cray system. Oh, I'm sorry, this was 2,000 of those nodes, my bad. 2,000 of the 5,000 nodes that they have. And they ran 2 simulations. One was a galaxy formation, and the other was a molecular dynamics simulation. And in fact, we demoed this at Supercomputing live. So Supercomputing was in New Orleans. We had a simulation running in Switzerland, streaming over the internet live in our booth in New Orleans. We were really scared on day one, so it turned out it worked really well. Now, this is a solution that you can implement today. So if you own an HPC cluster, you can get GPUs in it, and you can use them both for simulation and visualization. We have a recipe. We're happy to work with you to implement that recipe. And the basic idea is what I said earlier, but captured on this slide through pictorial here, which is instead of simulating, storing, visualizing, you can all do that in one kind of visualize it while you simulate system, right? I'm going pretty fast, and I'm okay to stop and take questions, or we can do it in the end. So I wanted to give you an update on our roadmap. Some of you follow us closely, so you may know what's happening. But let me give you a few things. Let me tell you about a few things. One is we launched a new product in November at Supercomputing. This is a product we call the Tesla K80. It's faster than any other product we've done before, as usual. And we have the benchmarks to show you. It's a speed up of 1.5 to 2x, depending on the application you were using, compared to our previous fastest product. It has a lot of memory in it. So one of the biggest feedbacks we get from our customers is, give me more memory on the GPU board. So we put 2 GPUs with 12 gigabytes each. And we also added this feature that we call GPU Boost. We found that in most real apps, there was a lot of headroom for the GPU to actually run its clocks higher. So even though we rate our GPUs at 225 watts, most times the GPU was running at, the board was running at 160 watts. So this actually boosts up the clocks of the GPUs and gives you this extra performance. And it does it automatically. Now, I like to show this chart because just to prove to the naysayers that the performance gap between accelerators and CPUs continues to hold and, in fact, grow. And I actually think there are 2 important metrics. People talk about flops. In fact, most real applications are more dependent on memory bandwidth than they are on flops. There's a balance, don't get me wrong, but memory bandwidth is as important and in many apps more important than flops. And we have a massive lead in both, right? And this is because we use, first of all, graphics memory today, and in the future we're going to use stacked memory, which will give us another boost. And then, of course, flops. Even graphics is just fundamentally a flops-based application. So K80 does really well on a range of real applications. So forget about the flops. Let's look at real apps. And I have kind of the synthetic benchmarks, right? You have LinPack and SGEM and DGEM. You have applications for molecular dynamics, quantum chemistry, and physics, right? These are measured in a lab. They're automated systems, so it's repeatable. We can give you the input sets if you want to repeat these experiments. Speedups typically with GPUs in a well-tuned app, so well-tuned for CPUs, well-tuned for GPUs, is between 5x, and in some case you get 10x. But 5x is a realistic speedup in apps that map well to the GPU. We have less, we have more. So let's talk about the next thing. So we use code names for our architectures. We're on the Kepler generation today. So all these products that I talk about, the K80, the K stands for Kepler. Okay? And we have a new GPU in the market called Maxwell right now. And next year we're going to have another GPU called Pascal. Pascal is actually a fundamental leap forward in GPUs. So Fermi was a big leap forward for us because we added double precision, right? We added real double precision. We called it our first computational GPU. Pascal is the next big leap, and because of 2 major things in it. One is we've added a high-speed direct interconnect on the GPU. This high-speed interconnect, I'll show you in the next few slides, enables you to connect GPUs to other GPUs and GPUs to other CPUs that have the same interconnect directly without going to PCIe. So you get 80 to 200 gigabytes per second. PCIe today is giving you 16 gigabits per second. So it's a dramatic speed up. And the other thing we're doing is we're going to stack memory. Stacked memory gives you up to a terabyte per second. The style we're using, the type of stacked memory we're using, gives you up to a terabyte per second of memory bandwidth. So let me put that in perspective. A single GPU today is about 300, let's call it 288, so roughly 300 gigabytes per second. And you get 3x more on stacked memory by going to Pascal, right? So as I mentioned, real apps, memory bandwidth is important. So let's talk about NVLink. This is, I believe, we talked a lot about exascale today in the panel, and I actually liked, I think, Addison, you said this, the difference between exascale and exaflop, right? One is the peak performance of the machine. The other is building a useful machine, right? Exascale means applications that take advantage of an exaflop machine, right? Otherwise, it's just a machine. It's a terrific LinPack machine, and it can be used once only. Now, NVLink is important because we have a lot of work that's been going on for the interconnect outside a server, right? Mellanox has been leading that. They have really high-speed interconnect to connect multiple servers. But within the server, we've been kind of bottlenecked by PCIe. And NVLink enables this, where today we have this architecture, right? We can connect to your favorite flavor of CPU via PCIe. In the future, you can connect two GPUs together via NVLink on that same PCIe architecture. Or if you use today the power CPU, and in the future we hope to get other CPUs up there, but you could then start connecting these CPUs and GPUs together via NVLink, right? So this changes the architecture within the node. And I'll come back to this in a minute. I first want to actually show you just what the value of this alone is. The reason is this is what we all use today, right? Most people are using x86 with PCIe and if you have a GPU in there. So what is the value of just this architecture where you have two GPUs connected via NVLink? So we did a simple experiment. We took two GPUs. We assumed there are 4 NVLink connections between them. So that's 80 gigabytes per second. And we estimated what the performance benefit would be. Just this versus PCIe. So imagine no connections between them. They're just connected via PCIe versus if they're connected via NVLink. And we found that the speedups just with NVLink could be anywhere from 25%. And this is actually just a kernel, but in real applications from 25% to 50%. So just the two GPUs communicating with each other. Right, now you can imagine a system with 4 GPUs connecting with each other, like this, right? So you could have clusters of 4 GPUs connected via NVLink, PLXed into an x86 or an ARM, and that could be connected to another one. So you can keep going on these clusters of 4 connected via NVLink and then connected to an x86. Okay, so the idea is that NVLink, at least even on your standard x86 architecture, can give you a lot of benefit on applications that are already GPU accelerated by enabling those GPUs to communicate directly, right? Now, if you insert a power CPU in here, in the next year's flavor of power CPU, that actually also has an NVLink connection. So you could actually have 3 GPUs and a power CPU in this same configuration to give you a much more tightly integrated CPU-GPU system. So the question is that because the workload's been distributed? Absolutely. A lot of GPU applications, the application actually runs on multiple GPUs by distributing the workload across. So a single instance is running across multiple, right? Typically, you're doing all kinds of halo exchanges or sort of the border communication exchanges. So communication between processors is critical. The programming model, the question is, will the programming model change? The programming model does not change. This is a simple load store directly into the other processor's memory. You can change the program to take more advantage of this. You may have structured the program assuming you have a slow link, but now that you have a fast link, you may actually be more forgiving about data transfers. It's a direct load store, yes. So you can directly load and store from the other GPU. Now this new, yeah, sure, wow. Yeah, so we have a feature called unified memory, which actually gives the programmer a view of the memory as if they're all one single memory space. So it's artificial, right? Because physically, the memories could actually be sitting across 2 devices and PCIe. Right? But underneath that, that means that the software compiler, driver, and runtime are automatically taking care of the memory transfers. So now if you have NVLink between them, whether it's a CPU or GPU or 2 GPUs, that transfer becomes extremely fast. But if that's right, right. Which will give you even further benefits, right? So if you have dual processors, do the processors, you mean the CPUs? Uh-huh. Right. No, so the core application is still running on the CPU. The question was, does the CPU lose control? The core application is still running on the CPU, right? And so this is a application level initiation of transfers, right? The difference is that those transfers are taking place much faster. It's fairly seamless from a programming perspective. I'm going to keep going and take questions in the end, although this was terrific. I am sensitive to the schedule here. Oops, right, that wasn't the right thing. That's the right thing. So this architecture of NVLink, along with our partnership with IBM and Mellanox, is in fact what is at the heart of the Coral supercomputers that the DOE is building. So Addison mentioned it briefly, but there are two systems that were announced, part of the Coral systems collaboration. One was the Summit system, and the other is the Sierra system at Oak Ridge and Lawrence Livermore. And these systems are expected to be anywhere between 100 to 300 petaflops, installed 2017. And just to give you an idea, there's an NVLink inside each server, and each node would be 40 teraflops. To put that in perspective, 3 of those nodes would make the top 500 list today. So 3 nodes in the Coral systems would make the top 500 list today. That's how powerful each one of these nodes are. Okay, so there was a lot of questions about when is exascale coming, when will we build the first exaflop machine. This is definitely a precursor, in our opinion, to what the architecture of an exaflop machine would look like. And that's why we've kind of laying the foundations with things like NVLink and the architecture that we're building with IBM and Mellanox. So this, I kind of spoke to you about this. There's a power CPU, there's interconnect via NVLink. I can keep going. And it uses our next generation GPU. Yeah, sure. I think these slides will be available on the website. Okay. Sure. So this Coral system will be built using Volta, and the question is, what's the difference between a Pascal and Volta? Volta is even faster than a Pascal, and that's all I'll say today. It's further out, so we're not revealing any more details about Volta at this point. We talked about exascale, and we talked about real applications. Everything that was done to determine what the architecture of these two machines started with apps. We started with a bunch of applications that were defined by the labs, and they said on these applications we want the following performance. That's how these systems were architected. It didn't start with LinPack, it didn't start with flops. It started with what was the scientific mission of these two labs. And you know that Lawrence Livermore is very much involved in national security, so a lot of their apps I can't even list up here. Now I'm going through a lot of stuff today, and I want to touch on deep learning because this is something that's very important and reasonably new. It is one of the hottest things that's happening actually within a 25-mile radius of this campus. There are roughly 50 startups that have been funded in the last couple of years in deep learning, many of them coming out of this university. And deep learning is essentially, so let's start with where it started, right? Or kind of give you a conceptual idea of what it is. I'm not a big photographer, but I probably end up taking, I don't know, a few thousand photographs every year, right? And I don't even have a DSLR, I have a simple camera. Many of us in this room probably take much more photographs every year. And the big thing is that these photographs are just being filed away. Most of us don't go back, look for them, and if we want to look for a particular photograph, it's just impossible. Wouldn't it be nice if all my photographs were automatically tagged? Automatically, it would say, here are all the photographs. I could just search dog, and it would show me all the photographs that have dogs in them. Well, that's the vision of what deep learning is trying to do. Throw at an algorithm just millions and millions of photographs, right? It'll analyze them, and it'll automatically tag all the objects in that photograph. That's what the kind of the purpose, or that's where it started, right? Now let's talk about the solution. I think this mic is on too, so we're getting a double. There we go. So deep learning is I mean, if any, all the folks here who did programming many, many years ago, we did neural networks. It was one of the things that you do, right? I mean, I think in my second year in my undergrad, I wrote a small neural network to recognize handwriting. So it would recognize letters, right? Many of us have done this. It's been around forever, and it has never worked, right? Neural networks has just not worked. And when I say not worked, not panned out as a commercially viable technology that is widely adopted until now. And now we have an approach, a new approach, which has, the idea is a multi-layer neural network. They call it a deep neural network. I like to think that it's deep because of the analysis it does. So what you do to this network or this model is you give it millions, if not billions of images, like this one. And what it starts doing is it starts with very, very deep analysis. And the first thing it determines, for example, in this case is, boy, edges are important. Let me find all the edges in all the images you gave me. And you didn't tell it to look for edges. It figured out that these edges things look like they're important, right? Then it starts putting these edges together and starts finding features. It finds eyebrows. It finds chins. It finds cheeks. It finds noses. Right? And eventually, it starts finding faces. And in fact, particular faces. So you can, for example, give it, for example, 6 or 7 or 8 photographs of me from different angles, different kind of perspective. And eventually, it can start recognizing my face in all kinds of situations. Lighting is usually one of the biggest issues. So the difference here is it's not a machine learning algorithm which is built on a heuristic, right? This is actually a model where it's learning itself. In many cases, it's unsupervised, in which what that means is that you're not even telling it what to look for. This was, in fact, what the original Google Brain YouTube video project was, right? They didn't tell it to look for cats. It found cats, because apparently there's a lot of cat videos on YouTube. So this is a really interesting new thing. And the reason why I'm excited, and so many of the companies out there are excited. I keep pressing the wrong button. Here we go. Is the impact it's going to make? But let me tell you why now, right? I was just mentioning, and I saw a few people nodding their heads on how neural networks didn't take off before, but they're taking off today. Why now? Three things changed. I'm summarizing at a much higher level, right? 3 things changed, right? And this, by the way. The funny thing is, this came in a Wired article. The Wired article said this, and in fact, it said GPUs too, so we were particularly happy about that. But it's the truth. 3 things changed. The amount of data some companies and some organizations has just exploded. People talk about big data. There are 500 million images being uploaded to Facebook every day. Okay, that's big data. That is truly big data. Now, you take all those images and you start doing feature extraction. With this new deep learning method, which is really a better model, a better algorithm, right? You can start extracting much more interesting information. But boy, you need to crunch that thing. If you have billions of images, you have to crunch through them like crazy. You can either buy 1,000 CPU servers like Google has, or you can buy 3 servers with GPUs in them, right? That Stanford can do, right? So the point being that these 3 things have been kind of the bedrock of this revolution of deep learning. Now, the impact of this is in many ways, right? I talked about image, but Spotify is trying to do music recommendation with this. Netflix is trying to do movie recommendations. Baidu is doing speech language translations. There is work going on in research. Today, if you look at how many cases cancer is detected, is you have scans taken, MRIs, CTs, and you have a doctor with a lot of experience look at them and say, yep, looks like a tumor, and whether benign or not, right? So you're now betting your life on the neural network in his brain or her brain, right? Instead of that, you can use a computer model which has been through billions of images, not just the thousands of images that doctor has seen, right? It's a completely different ballgame. So you can change, I'm going to go through my slides and then take questions if you don't mind. Yeah. So you can change the amount of data that goes through, and you can build these models. that can be much more effective. So there's, three things, but in fact, there's a whole bunch of stuff going on. There's folks doing speech. That's one of the very common use cases. Someone described to me today that deep learning is particularly valuable for analog data. What they meant was speech is analog, images are analog. That's particularly true, and I think it was a flip, which was those have been the hardest to analyze so far. So that's where you got this brand new big hammer, so that's where you're trying them first. But what we're seeing is we have Yandex doing search and indexing using GPUs now. You have all kinds of projects going on at many companies using deep learning and other kind of machine learning methods around GPUs. And of course, the universities are quite ahead in this area. So what's next? Deep learning, I think we've just begun. We don't even understand yet the kind of things we can do, right? I mean, there's some obvious ones, like I talked about the cancer or the medical use case. There's a lot of stuff that we can't, we haven't, people haven't thought through, or there aren't enough people working on it. Ideas for startups, right? Sentiment analysis is an obvious one, but what about, anomaly detection? A lot of problems on kind of security these days, on computer security. There's definitely companies looking at that. I know of a startup that's actually using deep learning for doing stock trading. They started off by actually offering a service, and they quickly realized, wait a minute, we can make money by just trading stocks ourselves, right, using deep learning. So a lot of stuff going on there. And the VCs have noticed. The VCs are funding this in big time. You can learn more about deep learning. We have a conference next month right here in San Jose, the GPU Technology Conference. Usually around 3,000 to 4,000 people show up here. The theme for our conference this year is on deep learning, right? So we, in fact, have about 50 sessions on deep learning this year from a whole bunch of who's who of people. You have a lot of the Chinese, leading Chinese internet service providers and consumer app companies. You can learn more at www.gputechconf.com. And we have also developer labs at the show. That was my last slide, and I tried to zip through everything really fast. So questions?